Now, if you want to read all of this right here, I'll just kind of leave it for you to do that. I'm not going to read you the story. But it basically walks you through kind of the steps in solving a related rate problem. And it's just a summary of some of the things we just did. There's a couple little nuances and variances that are different from the one we did in the warm-up, but you'll get used to them as you go. There's some geometric formulas, of course, that we've already encountered that you might need to know, like volumes of cylinders and stuff like that. So we're just kind of encounter all of these instructions as we go through the next problem. What is important, though, is at the very end, you make sure to smiley. Yes, smilly. At the end, smilly. Okay? Example 4. Here we go. Talk you through it. Example 4. An oil tank spills oil. Well, that's like 5 equals 5, right? That's what oil tankers do. They don't spill Mountain Dew. They spill oil. And they also don't just transport it without spilling it. They do spill it, right? It has happened, right? So an oil tank spills oil that spreads conveniently for us in a circular pattern whose radius, which we're defining to be little r, increases at the rate of 50 feet per minute. Oh. How fast are both the circumference and the area of the spill increasing at the moment when the radius of the spill is 20 feet? All right, so we're an investigative reporter. We're right there. We're watching it happen. And as soon as it's 20 feet, instead of jumping in and helping the aquatic life, we take a picture. And we take it back to our lab, and we sell that picture, right, to the highest bidder. All right, let's go ahead and draw a picture. I'm not going to draw an oil tanker, but I will draw the oil spill. Okay, so it kind of is going to expand out, and what are going to be kind of concentric rings, and I'm kind of drawing it kind of from an angle. And so at any given time, I'll just go ahead and say that that's going to be R, the radius of the spill. And I might want to go ahead and add some detail to it, you know. I don't know, something like that. I'm getting there. I'm getting there. And then, yeah, there you go. Something like that. An oil spill, all right? So the radius is really the only dimension that we need when we're talking about a circle, right? It gives us the diameter, it gives us the area, it gives us the circumference. So we've labeled that R as they told us to. Bless you. Okay, so now it's time to go ahead and kind of label the rate. It says blah, 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 increases at a rate of 50 feet per minute. So that would be dr dt, yes? And it's increasing, unfortunately, by 50. And if you want to put the units there, feet per minute. Most of the time, the units in the problem, they're the same units. Very, very infrequently are they going to give you like something in feet and then something like in inches, and you have to convert. They're usually the same. All right, and then it says how fast are the circumference and the area increasing when the radius was 20. So there's your snapshot moment. When the radius is 20 feet, we're there. We take a picture. And on part A, I guess we'll call it part A, we're looking for the change in the circumference. So I'm going to call the circumference C. So there's my target. And I need to then relate the rates to each other, dc dt to the r dt. But of course, before we relate the rates, we need to relate the quantities. So this is where it's real easy then, right? You're talking about a circle, and you want to relate the circumference to the radius. So the circumference is 2 pi r, piece of cake. That's your quote-unquote position equation. Once you have the position equation, we need the rate equation with respect to time, so we need to differentiate with respect to t. And we get on the left dc dt, and on the right we get 2 pi times the derivative of r with respect to t, which is dr dt. So a pretty easy little equation. Notice once again that the radius size, the actual size of the spill at any given moment, doesn't really come into play when you're talking about how fast the circumference of the spill is changing. It's only a function of how fast the radius is changing. It only has dr dt in it. But we're still going to reference the moment in time. So here we go. When r equals 20, we get dc dt, the rate of change of the circumference, to be 2 pi times 20, which equals 40 pi. And now in our final numeric answer, we include units. Dr dt is not 20. My bad. I'm making this more of a disaster catastrophe than it actually is. DRDT is what? 50. Actually, I was making it less of a disaster. That's my nature. Sorry. 2 pi times. Okay, lesson learned. Make sure you're plugging in the right quantity, right? You can kind of get on autopilot. I need to plug in DRDT, which is 50, not 20. Thank you. So it actually ends up being 100 pi. And then the units are circumference per time, so we measure that in feet per minute. And you can leave it in terms of pi. Okay, part B. At that same instant, how fast is the area of the spill? Okay, so that would be the coverage along the surface. So on part B, I'll slide up here. What variable is appropriate for area, maybe? A, good. Okay, good. The ADT. So that's my target. And now I need to relate the ADT to either dCDT or dRDT or both, whatever's convenient. Well, that means first I need to relate the area to C or R. Well, I think in a circle it's probably easier to relate the area to the radius, which is what? Area of a circle? Pi r squared. Okay, good. There's your quote-unquote position equation. Kind of the second verse to the same song. We'll take the derivative with respect to t. We get dAdt equals 2 pi r, which is the circumference, notice, interesting, times dRdt. So because the area is a squared quantity, its rate of change is dependent upon the actual size of the radius at the given moment. R is a variable in the equation. So now we'll plug in when r equals 20, dAdt equals 2 pi times r, there's the 20, times the 50, and now we get a big number. 4 times 5 is 20, with 2 more zeros, times pi, 2,000 pi. And the units are area over time, so that would be units of square feet per minute. Huh? 2,000 pi? Good year? Good year, good year. Yeah, it is a long ways away. These numbers were ripped from the headlines. Okay, so if we want to write a sentence, we kind of know some information about this at the moment. We could say when the radius of the spill is 20 feet, the circumference is increasing by 100 pi feet per minute, while the area is increasing by 2,000 pi square feet per minute. Okay. Now, of course, unfortunately, oil doesn't tend to mix well with water, right, or with aquatic life. But oil, you know, floats on the surface, but because it is so heavy and dense, it can actually succumb to its own weight, and of course, it starts to sink. It starts to submerge under its own weight. And so, let's read on, okay? That's possibly where it does most of the damage, right? If the depth of the oil spill, yes, sinking oil, is given to be this. Now notice it's a variable equation. If the depth of the oil is given as a function of the radius, that's very convenient, okay? 2r squared plus 1. How fast is the volume of the oil spilling at that exact same moment? Well, that's interesting. I am going to call this part C, and the rate of change of the volume, I'm going to go ahead and take the liberty again of calling the volume V. So I'm looking for dV/dt. So what I would like to do now is somehow relate the V, the volume, to the radius and or the depth. I use d of r for depth. Well, volume is 3 dimensions, right? So if you think about this idea, and this is a pretty important idea, if you think about just like a geometric prism, like a cylinder, right? The way to find the area of a three-dimensional object that has a regular face is to, or base, is to take the area of the face, right? And maybe it's a function of a variable, and you multiply it by the height, or in this case, we could say maybe the depth at any given moment, right? So that's the idea here. So the volume of the oil spill is going to be the area of the surface, which we know conveniently is a circle, so that's going to again be pi r squared, times the depth at any given value of r, which conveniently was given to us, thank you very much, 2r squared plus 1. So that gives you your third dimension. So it's the area times the depth. And because it's a function of r, it makes it really nice. Now, if you want, you can go ahead and expand that. You get 2 pi r to the fourth plus pi r squared, just so you can use the power rule, maybe, when you take the derivative. Okay, so let's go ahead and take the derivative then with respect to time. And we get dv dt equals, let's see, 8 pi times r cubed times what? The r dt, yeah, don't forget that. Plus 2 pi r times the r dt. And now all we have to do is plug in. So when r equals 20, I'm going to go smaller here. We get dv dt equals, okay, so we got 8, we got pi. The radius at the moment was 20, so that's 20 cubed. The r dt was 50. And then 2 pi r dt, that kind of sounds familiar to me. Did we already do 2 pi r dt at 20? We did. That's going to come out to be 2,000 pi. So if you recognize that, you can just substitute that in. And we'll go ahead and maybe finish this up without a calculator. 20 cubed, that's going to be a big number. 8 times 5, that's 400. 20 cubed is 400 times 20. 8,000 pi plus 2,000 pi. And so here we get 32 with 5 zeros. Wow, that's 3 million. Poor wildlife, aquatic life. Now, if you want to add those together, those are like terms. So you get 3,202,000 pi. Wow, cubic feet per minute. And yes, that's realistic. So what might that look like, that 2r squared plus 1? If you're looking at it from the surface, or maybe horizontally to the surface, I should say. The surface looks like a circle, but maybe, you know, the oil is kind of, it's right here, like in a circular pattern from above. Maybe, you know, as it's leaking down, it's looking something like that. It's kind of looking like a parabola. And the depth at any given value of r would be a function of r like that. So that's what's happening, which makes sense. It's kind of, you know, thicker in the middle, so it's kind of seeping down at this irregular rate. So anyway, maybe not necessarily actual numbers, you know, taken in the field, but the idea behind it is kind of the same. Now, that's only good at that one instant, you know. So anyway, it happens, right? It happens. And if you're Kevin Costner, you invent something to clean it up and you become a millionaire again. Yeah, which actually happened. Okay, good question. This little part C. No, in real life. Yeah, that BP oil spill. Kevin Costner invented a skimmer that actually went through and cleaned it up, and it was very lucrative for him. Kevin Costner, the actor. Yeah. So anyway, yeah, that actually happened. Pretty cool. Okay, any questions on example 4? All right, my favorite problem, example 5. My favorite problem. Okay, just looking at the scenario, I mean, so much you could say about that. Just, I mean, it's the dude at the top, right? I mean, like, what did he take that morning? And the dude at the bottom, I mean, what is he up to? He's not fooling anybody either, you know? Yeah. So anyway, let's read. Shenanigans taking place. A 10-foot ladder is leaning against the vertical wall. The lower end of the ladder is being pulled away from the wall at a rate of 2 feet per second. I wonder who's responsible for that. Yeah, that smile doesn't fool anybody. Okay. When the lower end of the ladder is 6 feet away from the wall, So that's your snapshot moment. So there's a third guy here taking the picture, right? This guy is going to be oblivious to everything, right? It's, even when it hits the ground, he's going to be like, "Whoa, what happened, dude?" All right. Okay. At that moment in time, how fast is the ladder sliding down the wall? In other words, how fast is that dude sliding down the wall, right? What kind of velocity is he experiencing? His physical body, not in his mind. He's probably experienced something else. Okay, so we draw a picture if there wasn't a picture already drawn. And they've already labeled some of these things for us, which is nice. So this is the distance away from the base of the wall, and they're calling that x. And it's changing, so we have to call it a variable. The distance that the ladder is resting up against the wall, they're calling y. And it's changing, so we have to call it a variable. We can assume that the wall is at a right angle to the floor. The ladder then forms a hypotenuse to this, what will be this right triangle, yeah? Now, does the length of the ladder change? No, we could assume it doesn't. That would make for a much more interesting problem if it was like an extension ladder and it was changing. If something does not change throughout the life of the problem, you don't have to call it a variable. You don't have to call it L for ladder. You can call it 10 for ladder. Okay? 10. Now, our snapshot moment is the following. Here's the snapshot moment. The snapshot moment is when x equals 6 feet. Okay? That's your snapshot moment. And I left a little room in the camera. Why? Because I could go back to my mathematical lab, and at that moment, I can calculate what y is, or was, okay, in the past. So let's go ahead then and do what we normally do, just kind of setting up the problem. We drew the picture. The variables are defined. We want to go ahead and label the rates. 10-foot ladder, blah, blah, blah. The lower end is being pulled away. All right, so the lower end being pulled away is going to be the rate of change of what variable? X. It's directly changing X. So that's going to be dx dt, and it's being pulled away at a constant rate, we can assume, of 2 feet per second. So is it going to be positive 2 or negative 2? It's being pulled away. Should be positive. All you have to do is ask yourself, is X getting bigger or smaller? X is getting bigger, right? So it's positive 2. So dx dt is positive 2. All right, on part A, how fast is the ladder sliding down the wall? That's basically looking for the rate of change of which variable? Y. Okay, so now we have our target. On part A, I'm looking for dy dt. That's my target. So now, before I can relate the rates, dy dt or dx dt, I need to relate the quantities. So in this picture, what's the quickest, fastest, easiest way to relate x to y? In this right triangle. Pythagorean theorem. Yes. Good. So here we go. We got x squared plus y squared equals ladder squared, which of course is 10 squared. It's a constant. If it changes, got to be a variable. If it doesn't change throughout the life of the entire problem, constant. All right, so there's your position equation. Of course, if you want to call that x squared plus y squared equals 100, or you could have done that in the beginning, that's fine. Let's go ahead and take the derivative with respect to time, and we'll just do it implicitly. We won't solve for y or anything. So here we go. We got 2x times the chain rule, dx dt, plus 2y times the chain rule, dy dt, equals the rate of change of the length of the ladder squared, which is 0. Yeah, the ladder's length isn't changing, so neither is it squared. All right, so if you want to, just like we did yesterday with the Pythagorean theorem, there is a 2 that is common factor that you could divide out all the way through, and you can end up with a maybe nicer version. X dx dt plus y dy dt equals 0. And if you want to solve that explicitly right now for dy dt, that's fine. That's your prerogative. You could do that. I'm just going to go ahead and leave it like this as my rate equation, and then I'll plug in and then solve. All right, so now we're ready to plug in. When x is 6, there's the moment in time, we get 6 times dx dt, which we define to be 2, if you remember, plus y. Oh, shuckaroonies. I need to know what y is at that exact moment in time. Well, no problem. That's where my position equation comes in. So at that moment, remember, when x was 6, we get 6 squared plus y squared equals 100. So y squared equals 100 minus 36, which is 64. And we consider plus or minus, but we're talking about length above the wall, so we have to be the positive value. So y is equal to 8 at that moment. All right, so I'm going to come back over here to my camera, and I'm going to put that in there. That's at the exact same moment in time. So I didn't find it at first because I didn't think I would necessarily need it, so I found it when it came up, when I needed it in my calculations. But now I have it, so I'll go ahead and put it in here. So that's going to be 8 times dy dt, which is what I'm trying to solve for, and that equals 0. So now it's algebra 1, right? You get dy dt equals, if you go 6 times 2 is 12, subtract it, it becomes negative 12 on the other side, bless you. Divide through, you're welcome, by 8. We get that, and then I'll simplify, and I get dy dt equals negative 3 halves. And because it's my final numeric answer, I'm going to go ahead and put units on it. We are talking about the whole time feet, and time is in seconds. So feet in seconds, feet in seconds. So that would be negative 3 half, bless you, feet per second. Now it's a negative number. Is that reasonable? Yeah, because y is the distance above the ground, and since the ladder is sliding down the wall, the distance y is getting smaller by 1.5 feet per second at that moment. Now dx dt was given to us, so we have to assume that dx dt is a constant rate. We're assuming that this is a constant rate because it didn't say otherwise. We just calculated dy dt. Is dy dt a constant rate? No, yes? Or yes, no? Well, let's look at the equation, right? To compute dy dt, back up here, I need to know dx dt, which is a constant, right? But I also need to know what? X and y. And it's only going to be a constant if x and y are constants. Are x and y constants? No, x and y are changing as the ladder slides down the wall. So dy dt is actually not a constant. It changes depending on what x and y are. And if you kind of imagine what's happening here, the speed of the ladder down the wall is actually increasing, right? If you have it up against the wall and you pull it away at the base at a constant rate, when this ladder is straight up against the wall, most of the energy is being used for the horizontal pull, and it's sliding down the wall very slowly. But once it gets past maybe the halfway point, now a small change, because the lever is getting longer really, a small change in the ladder is going to mean a big change in y. And so if you're pulling away at a constant rate, that ladder is going to go, can I use your desk? Yeah, it's going to go bam on the floor, like really hard, like this. Watch, like here's the ladder, right? It's going to come down and go like that. Oh my gosh, right? And who's at the top? That dude, right? And I wouldn't want to be his ankles, and I wouldn't want to be him the next day. Yeah, when the stars leave his eyes, right? Okay. So it's going to be painful. All right. So anyway, there we go. We answered the question for part A. Part B. Thank you, Juan, for volunteering your desk. How fast is the angle between the ground and the ladder changing? The angle between the ladder and the ground. The ladder and the ground. Okay, that's this one here, right? Kind of important to identify the right one. What do you want to call that angle? It's changing, right? Is it getting bigger or smaller? It should be getting smaller, right? So its rate of change should be positive or negative? Negative. Okay, cool. What do you want to call it? A for angle? Theta for angle? I kind of like theta. If you want to use something different, feel free. I'm going to call that theta. So now on part B, I'm giving myself my target. I'm looking for d theta dt. So now before I can relate the rates, I got to relate the quantities. I got to get theta involved somehow in this picture. In the right triangle, how do you get theta involved? Yeah, perfect. Trigonometry, yeah? And you have 6 trig ratios from which to choose. You chose sine. Sine is going to be opposite over hypotenuse. So you would say that sine of theta is y over 10. That would work. That would be beautiful. That would be perfect. Y would be something that we would need to know at the moment, which we found it. When we take the derivative, we're going to need to know dy dt then, which we just computed it right here on part A. So we would then use the values that we found. So that would be one way to go. And when you use dy dt in the next calculation, you would just fingers crossed, I hope it's right, yeah? That you didn't mess up on part A. And of course, we're all confident, and we're all each other's witness and alibis, so that should be correct. But when you're working on your own, maybe you're not so sure. So although sine would work, what I would probably recommend is maybe to use the values that were given, just in case. We were given x and we were given dx dt. So sine would work perfectly, but maybe cosine would be a little bit better, or safer, I should say. So that would be adjacent over the hypotenuse over 10. Now, I wouldn't recommend using tangent, because tangent would be y over x, and it too would work, but that also introduces another variable. So if you can get the hypotenuse involved, which is the length of the ladder, it's a constant, it'll eliminate one of the variables in your equation, which means it'll make the derivative a little bit easier. So it was good to get 10 involved. All right, so from there I could take the derivative if I want. I'm going to go ahead and clean it up, though, just a little bit. I'm going to multiply both sides by 10. Since I'm taking the derivative implicitly anyway, I'll leave it like that. So you have that option, or look, you could do this. You could take the inverse cosine of both sides and solve it for theta first. Do we know how to take the derivative of arc cosine? We do. So you have that option if you want. You want to go that route? You go that route. I'm going to go the other route. We'll compare answers at the end. Okay? It works. It works. What is the derivative of negative or arc cosine, by the way? It would be negative 1 over the square root of 1 minus blob squared. Good. Times the derivative of the blob, which is 1/10. dx dt. Yes, we needed dx dt right here. Thank you, thank you, thank you. We have to remember that we're taking the derivative with respect to t constantly, which is easy to do. So I don't know if y'all want to do it that way. We kind of just did. Yeah. This one is nice because it does only require the value of x and dx dt, which were given. So let's go ahead and just keep doing it this way. So when x equals 6, d theta dt equals, all right, we get negative 1 over the square root of 1 minus, let's see, 6/10 is also known as 3/5. And 3/5 squared is known as 9/25. Woof, good. And then there's times a 10 in the denominator times dx dt, which is a 2, which I'll put it in the top. The chain rule, yeah, easy to forget here. And if I simplify that, that's a negative 2 over 10 square root of, well, let's see. 1 is the same as 25/25, yeah? So 25 minus 9 would be 16. So that the denominator becomes the square root of 16/25. The square root of 16/25, that's a perfect square. That's 4/5. Wow. This is turning out to be a nice little number here. And in the bottom here, in the denominator, 10/5 is also known as 2. The 2's then divide out, and you get negative 1/4. Oh, wow. Nice. Nice. Yeah, thanks, Nick. I like that. You know, in all the years, we've never done it that way, ever. We've never, ever done it that way, or I've never done it that way. Now, what are the units? It's units of angle over units of time. Degrees per second? Degrees. Well, remember, the units have to come out of the calculations, right? So if you're having degrees in your final answer, where, when we plugged in, did we get degrees? Did we plug in anything in here that had units of degrees? I don't remember doing that. Degrees don't just appear out of nowhere when you're talking about angles. Sorry, folks. Radians are the ones that appear out of nowhere when you're talking about angles. Because they're unitless, right? It's a ratio. So those are radians. Very good. Radians per second. Now, if you wanted to convert it to degrees, let's go ahead and see what that would be. Negative 1/4 radians per second. You could multiply by radians and degrees. And what's the conversion factor? 180 over pi. So, yeah. You want to do that? Does it say what? It just says how fast is it changing. I'll go ahead and do it. I have a calculator right here. We could probably appreciate degrees a little bit better than radians, right? So negative 0.25. It is negative. That's good. Times 180. I'll go ahead and divide it by pi just to get an actual answer. And let's see. If I typed it in correctly, I got negative 14 point. How many decimals do we need to report? Good. So it's 3239. So what answers would be acceptable? I put 4 there. Negative 14.323 or negative 14.324. Yeah, you can round or truncate. Round or truncate. It doesn't matter. This one here, there's no degrees on it. Yeah, that one. Oh, yeah, per second. Awesome. I kind of forgot what we're doing. Huh. Okay, yeah, I forgot what I was doing. Yeah, per second. So if we then try to say the sentence, which maybe I'd catch it by then, when the ladder is 6 feet away from the base of the wall, the angle between the ladder and the ground is decreasing by about 14.324 degrees per second. Okay, cool. What was the other way to do it? Well, if you leave it like this, and you take the derivative with respect to time, you get dx dt over here, and you get negative 10 sine of theta times d theta dt. Now, when you plug in there, notice you don't need theta, you just need sine of theta at that moment, right? And if you come back over here to this picture, if you want to fill in at the moment, x is 6, y was 8, at that moment, all you would need at the moment would be the sine ratio, and the sine ratio would be 8/10, right? Which is also known as 4/5. So then you could plug it in here and get 2 equals negative 10 times 4/5 times d theta dt. And that makes the math just a little bit easier, but it works just the same. Okay? Cool. At any rate, we got the answer for that. Are we done with the problem? Not even. Not even. Yeah, we're halfway done. Part C, how fast is the area of the triangle formed by the ladder and the 2 walls changing? So the area, that's the whole thing right there, the whole area. Okay, well, let's call this part C right here. We're looking for the rate of change of the area. I'm going to call the area A. So we're looking for dA dt. So in a right triangle, I need to relate the quantities, and I'm calling my sides x and y. So what would be the area of the right triangle? We did it yesterday, right? 1/2 base times height. So that's going to be 1/2 x times y. And we have 2 variables there. So we get to use the product rule. So the derivative with respect to time would be dA dt on the left. And over here we get 1/2 dx dt times y plus 1/2 x times dy dt. Now, there's a lot of information in there. But it's solved. It's nice that it's solved explicitly for the one that we want. So we'll plug in. When x equals 6, all that same moment in time, the dA dt is going to equal 1/2 is a half. I got that. Dx dt, if I remember, was 2. We notice we need y at the moment. We already calculated that in our mathematical laboratory. That was 8. We did a little forensic work there and discovered that. We have a 1/2 here again. We know x at the moment is 6. And darn it, we need dy dt. We need to know how fast the ladder was sliding down the wall. Do we have that? Yeah, we actually discovered that right up here in part A. So if I really wanted to know how fast the area was changing and I hadn't done this calculation yet, I would need to go off to the side somewhere and do that. -3/2. Good thing we did it first. -3/2. And that would be square feet per second. Let's see where we are in terms of the ladder being pulled out. The ladder's 10 feet. When it's 6 feet from the wall and it's 8 feet high, it's before the halfway point, the 45-degree angle, or at the 45. It started up against the wall, I guess, and as we're pulling it out, since it's still higher on the wall than it is away from the wall, it's not quite yet at the 45, right? So at this point, do you think the area should be increasing or decreasing? What do you think the most optimal right triangle would be at? What angle? Maybe the 45, right? Nature loves symmetry. So at this point, if it starts off against the wall, the area is 0. The area should be increasing up to a certain point, right? Maybe at the 45. And then after the 45, then the area should be decreasing back down to 0, right? So it goes from 0, big, and then it starts decreasing back down to 0. So at this point, the rate of change of the area, you think should be positive or negative? Probably positive, yeah. Let's see what the calculations tell us. I get 8 here, and I get plus, that's a 3 times 3, that's going to be a minus actually, 9/2. 8 minus 9/2. Well, that's going to be 16 minus 9, which is 7/2, which is positive 3.5, whatever you want to call it, square feet per second. Yeah, positive. Cool. So it's nice to think about, you know, what the answer might be before you get the answer, or after the fact, maybe you just see if it's reasonable. Okay, and then one last little section here. We said that the ladder sliding down the wall was not a constant, that it was in fact speeding up. It was speeding up. It was accelerating down the wall, right? What is the acceleration then of the ladder down the wall? Now, before we start again, let's think about it. The ladder is accelerating down the wall. Would you agree? Speeding up. If the velocity of the ladder down the wall, which we found in part A, that's its velocity down the wall, is a negative number, and the speed is increasing, then what should the sign of the acceleration be? Also negative, right? We've talked about that. Speed is going to be increasing only when the sign of velocity and acceleration are the same. So if the velocity is already negative, in order to get it to be speeding up, the acceleration also has to be negative. So we're expecting a negative number. So what do we start with? We're looking for really the second derivative of y with respect to t, right? That's what we're looking for. That would be the acceleration down the wall. Okay, so what do I need to do? I need to retreat back somewhere and get my first derivative equation, which we have right here on part A. So I need to reuse that. Now, with Notability, I can just copy it and paste it so I don't have to keep going back and forth with tunnel vision. If I have paper, I can just look up there and rewrite it. Now, there's one key thing that we want to do before we jump in and take the derivative, maybe two key things here. If I need to take the derivative, I could use the product rule here, but since I'm looking for the second derivative, maybe here is where it's worth solving for dy dt. Because when you start taking the derivative of derivatives, it gets kind of cumbersome. So let's go ahead and do kind of like what we did back when we studied implicit differentiation. Let's solve for dy dt first. We'll subtract that term, and we'll divide through.
Please make sure to return all signed report cards, rosters, along with any unsigned report cards to the back office by the end of this period. Also, NHS candidates are reminded that all candidate information, including the application, references, and documentation of service hours, are due on or before Friday, January the 8th, 2016. If there are any questions, please see Ms. Gray in room 103. Also, the following students can report to the back office to take up their perfect attendance. certificate.
Free Whataburger Jr.
Danielle Almendarez, Corey Carr, Stephanie Cook, Rachel Emerson, Bianca Garabee, Amber Gaitan, Esmeralda Hernandez, Sienna Herrera, Lauren McLean, Wesley Moran, Benjamin Rodriguez, Ariana Sandoval, Sarah Scroggin, Patrick Spellman, Mitchell Taylor, and Jordan Westbury.
At this time, if you could please turn your TVs to Channel 4 for the morning announcements. You can also view them online at mbhstv.com.
Okay. So we saw for dy/dt, and if we jumped in now to take the derivative, it would appear that we have three variables, and that would be like a Hody high with a product rule in the numerator, yucky, yucky, gross, gross. So maybe you'd prefer to actually come back here and just do two product rules. But remember when we set up the original equation, we had x squared plus y squared not equals ladder squared. We had 10 squared. And why could we plug in a 10 for the ladder instead of calling it L for ladder? It's a constant, okay? So what you also want to do then at any time before you're taking the derivative is determine if there are any constants in your equation that may already be called variables. X is not a constant. It's changing. Y is not a constant. It's changing. But what do we know about dx dt? It is a constant, right? Dx dt is a constant. So you could actually plug that in before you take the derivative. And what was dx dt? It was 2, right? So that becomes negative 2x over y. Okay, so if you actually wanted to find how fast the ladder is sliding down the wall now at a different moment in time, that could be like the explicit equation now that you plug into. And of course, if you plug in a 6 for x and a y for 8, you get what we got in part A, negative 3 halves. Let's go ahead and take the derivative of that now. The derivative with respect to t, the left side becomes d squared y over dt squared, which is what we want. And now it's a relatively easy Hody high rule. We get ho, and then d high is going to be negative 2 times dx dt. Hody high minus high, so careful, it's minus the negative. I'm just associating the negative with the top. It's a little bit easier. Hody high minus high. D ho is dy dt all over ho ho, which is y squared. And now we can say when x equals 6, we get the second derivative of y with respect to t, also known as the acceleration of the ladder. We'll plug in, and hopefully we know every variable on the other side, and if not, we can go off to the side and find it. At the moment, y is 8, we know that. Negative 2 is negative 2. Dx dt is 2. Minus the negative becomes plus. 2 is 2. At the moment, x is 6. dy dt, we calculated it in A. Here we need it again. It was negative 3 halves all over y squared, which was 8 squared. And with a little bit of elbow grease here, we can simplify it. We get negative 32 minus 18 over 64, which gives us negative 50 64ths, which, gosh, that may simplify into something, huh? Negative 25 32nds. And it is a negative number, as we expected it would be. And now what are the units? Feet per second squared. There you go. So when the ladder is 6 feet from the base of the wall, it's sliding down the wall at 1.5 feet per second, but the acceleration is negative 25, 32 feet per second squared. So that's how fast the velocity is decreasing. Okay, cool. That's an excellent problem because one simple little situation, it's basically one right triangle, but yet we can ask so many questions or discover so many things about what's happening at that instant, okay? And it would be good maybe to figure out what happens later on. I don't know, but we've never written a chapter to this story. So we don't know how these guys got here, and we don't know what became of either of them after the story is over. But they show up every year, so they must be okay. They must be okay. They must have survived the incident. All right, we'll stop right there for the day. I don't know. I would like to ask them if they were real. I would like to ask them what the heck's going on.